Hi folks, Mr. Ackerman here. Thanks for watching. The topic of today's video is inertial and non-inertial frames of reference, and we're going to be finishing up the chapter with this lesson. So if you take a look in the homework schedule, you'll see we're in lesson 4 right now. The section in the textbook, that's Physics 12 by Nelson, is inertial and non-inertial frames of reference. This term, frames of reference, might ring a bell. We did talk about this in the last, or one of the last lessons of the last unit, or the last chapter, and I will point out some of the similarities. But as usual, make sure you read along in the book and take some notes if you can. Pay attention to a couple of sample problems, one of which I'm going to show you today. Also some homework questions to try in class, and also some for after class. There is a lab in this section, and I'll be discussing that with you in class. We'll probably do that. It will take one day probably to do some problems in class, and then another day to work on the lab. And finally, there is a YouTube video which I'll reference in this video. This is a continuation of the frames of reference videos that you saw last time we talked about frames of reference. I'll explain in a minute. And finally, the learning goals and success criteria are down here. By the end of today's class, you ought to be able to do everything that you see in here under the success criteria. This will make more sense, some of these terms, after we're done with today's video, and the rest, the ones referencing the lab here, will obviously make sense once you've done the lab. All right, so just a few quick questions to get us started. As I mentioned in the title, we're learning about non-inertial frames of reference. And you've heard the term inertial frame of reference before. I mentioned that when we talked about the special theory of relativity, and I talked to you about the two postulates that Einstein made. If you think back to what they are, or what they were one, that the speed of light is constant for all inertial observers. And at the time, I said to you, don't worry about the word inertial. Yeah, it has something to do with inertia, which you've heard about, but for now, it just means moving at constant velocity. Of course, the second thing that he said was that physics is the same in all inertial frames of reference, and there was that term again, and you kind of knew what it meant, but you kind of didn't. Well, today we're going to find out by looking at non-inertial frames of reference. Once you know what a non-inertial frame is, you'll understand what an inertial frame is. We're also going to be talking about forces here, so free body diagrams are going to arise, and we're going to look at motion viewed in two different frames of reference, the same motion, and how this results in two different free body diagrams. So this is going to get a little tricky, but hopefully you'll be able to wrap your head around it by the end. And finally, we're going to look at solving some problems in these non-inertial or accelerated frames of reference. All right, so without further ado, we're going to move on to our first slide here. And now I've already talked to you a little bit about what we did in the past when we talked about frames of reference, but let's just think back to what we learned. Maybe the most memorable video was what I like to call the Japanese Mythbusters video. And this was the one where, if you recall, these Mythbuster type guys from Japan were driving along in a car. And so let me just get us a car. There we go. And if you recall, they took a baseball out of a baseball pitching machine, actually, and they launched this baseball backward out the back of the truck, and it was moving with a velocity of the ball with respect to the truck of something like 100 kilometers per hour. Of course, the truck itself was moving forward with a velocity also of 100 kilometers per hour, but this was the velocity of the truck relative to Earth. So let's just put that in there, 100 kilometers per hour. And of course the question was, if you're standing on the ground and you are filming this, which is basically what you saw from the camera's point of view, what do you measure as the velocity of the ball relative to Earth? And the whole question, I suppose they were speaking Japanese, so I don't really know what they were saying, but I can imagine they were saying, if the truck is going this way and the ball's going that way at the same speed, will the ball hang motionless in the air? And this is what they wanted to resolve. And of course it did. And so we realized there's a formula that you can write here, and the formula goes something like velocity of the ball relative to Earth equals velocity of ball relative to truck plus velocity of truck relative to Earth. And sure enough, this formula worked out. We used it in 1 dimension, and we used it in 2 dimensions. We talked about airplanes and airspeed and wind speed and ground speed, and we talked about canoes going across moving rivers and all that stuff. Everything worked out fine. However, the important thing to note here was that we were talking about motion at a constant velocity. In other words, all of these ideas were in a special case of 2 frames of reference in motion relative to one another, but at a constant velocity. Is the case the same when one of the frames of reference is accelerating? Well, as you're going to see, things are quite different. And the idea that all of the physics that we can do in accelerating frames of reference, will that be the same as the physics we do in non-accelerating frames of reference? Well, I'll let you be the judge. The first thing I want you to do at this point is in a moment you're going to pause my video and go watch another video. So if you look back in your homework schedule, it says to click on this link here and watch the continuation of that black and white video called Frames of Reference from about the 4.5-minute mark onward. There's only about 4 minutes remaining in this video, so that's all you got to watch. It is, let me just go to it here. There you go. This is what it's going to look like. And you can just click on around 4.5 minutes, okay? And watch this guy. Just watch this till the end and come back when you're done. So pause this video now, go to that. Okay, I'll assume that you're back and you have watched this now, and so you are returning with me over here, and you've just watched this video where maybe the ideas that you learned back when we did frames of reference for the first time suddenly don't make so much sense. For example, in the video that you just saw, here's a little screen capture of part of it. The most memorable part, I imagine for you, was when the cart was accelerating onward, and the ball, instead of falling straight down like it used to, actually fell backward on an angle. And the professor here, I think this is Professor Hume. It's Professor Hume or Ivy. I can't remember which one. I think he's Hume, but you can check that. He mentions that it seems as though there's some backward force acting on the ball. So let's draw this ball as it falls down. There it is. We've got a ball falling down, and now what do we know? Let's always start with things that we know. We know that the force of gravity is certainly acting on this ball, so we can write that in there. And, well, there's no strings attached to it, so there's no tension. There's no magnets or anything electromagnetic that we can think of. Certainly there's no nuclear forces involved here. There's nothing nuclear going on in this question. There's no friction. There might be a bit of air resistance, but I mean really not a heck of a lot. After all, that cart wasn't going that fast. And in the previous video, or the earlier on when we dealt with frames of reference, the ball did fall straight down. So why is it going backward now? Well, you and I believe in Newton's first law, the law of inertia. I like to call that N1 for short. What does N1 tell us? It tells us that your velocity is constant unless the net force is not zero. In other words, unless there's an unbalanced force. Well, vertically, the velocity is not constant, but I can live with that because the ball is accelerating downward due to gravity. So I'm cool with the vertical acceleration. That's due to gravity. The part that I don't get, if I'm someone who believes in Newton's first law, is this backward acceleration of the ball that I observe. After all, what force is causing it? If I believe in Newton's first law, then I've got to believe there's some force here. The problem is, we've learned in this course that there are 4 fundamental forces. And none of these forces can explain what just happened to the ball as it fell. So we're left with a little bit of a problem here. Either we invent a new force and we get to still believe in Newton's first law, or we have to decide that in this strange frame of reference, Newton's law simply does not apply. So what's your choice? Do you want the red option where I put a red X through Newton's first law? Or do you want the brown option where I get to agree with Newton's first law by inventing some force that is not one of the 4 fundamental forces? This is not a fun situation to be in. We don't want to disagree with Newton, but we also don't want to start inventing forces. Well, what we end up deciding in the end is one of these two things has to be wrong. Well, we're not about to start inventing new forces that are kind of magical, so we don't have to get rid of Newton's first law. We can actually keep Newton's first law and be happy about it. The way we do that is by saying, in this frame of reference, Newton's first law does not apply. Newton's first law is still true, but in this FOR, in this frame of reference, that's where Newton's first law does not apply. And so we have a name for that. Since Newton's first law is called the law of, oops, let me try to get that W there. Since Newton's first law is the law of inertia, therefore, in this frame of reference, where the law of inertia simply does not hold, we'll just call this a non-inertial frame of reference. And then we'll be able to go to sleep at night without worrying too much. It's not that Newton's first law has been proven wrong. We get to keep it. It just doesn't apply in every frame of reference. It only applies in inertial frames of reference. What are examples of inertial frames of reference? The Japanese Mythbusters. Constant velocity. That's an inertial frame of reference. The Earth is a pretty good example of an inertial frame of reference. It's true that the Earth is spinning and therefore there's some acceleration. It's true that we're orbiting the Sun and therefore there's some acceleration. But these accelerations are so tiny compared to what is needed to result in these strange forces that we can practically ignore it. The Earth is therefore, for most purposes, an inertial frame of reference. Being in an airplane flying from here to Barbados for winter holidays, that's an example of an inertial frame of reference. You're moving at a constant velocity. And if you think back to a previous video where I discussed frames of reference, I gave you the example of what would it be like if you were pouring coffee at 35,000 feet on that airplane compared to pouring coffee at the airport on the ground. Would the physics be any different? No, it wouldn't really be any different. Both frames of reference are inertial. The laws of inertia apply. It's like everyday coffee pouring, everyday physics. However, what I want you to do now is the following. Next time you're in a car, and preferably not the driver, so maybe if you're getting a lift to school tomorrow morning, or you're going out somewhere tonight and someone else is driving, here's what I want you to do. I want you to sit in the passenger seat, and I want you to pay attention to what the driver's doing. When the driver is at a red light and waiting for the light to turn green, and then the light does turn green and the driver begins accelerating forward, I want you to think about, actually I want you to do this, I want you to take any object like your smartphone or a coin or a pen or anything that you have and just try to drop it straight down. As the driver accelerates, can you think of what's going to happen? Maybe you've done this before. Think about it for a moment. Pause the video if you have to. And now we're back. So the car is accelerating forward. You're dropping an object straight down, maybe into your lap. Can you see how it's actually going to land? It's maybe going to hit you in the stomach. It's going to sort of fall a little bit on an angle backward toward your body. In other words, it's going to do exactly what you saw in this video here. It's going to have some strange force pushing it backward. And you might think, oh, there was a force acting. But wait a minute, what kind of force? Certainly not one of these. Are we going to start inventing forces? No. We're going to understand that Newton's first law does not apply in the car's frame of reference when we're accelerating. Because remember, we were accelerating off of a red light that turned green, and that's why this happened. Here's another example that is very graphic and which I'm sure all of you can relate to. We get in a car and we're told to wear our seatbelts. Here's a screenshot of a YouTube video. It's not in your homework schedule, so go to this right now. It's called Inertia Within Car Collisions by Chosen Taco. I don't know where he chose that name, but it sounds pretty good to me. Here we go. Let's have a look. This is a crash test dummy video. You're going to watch two cars which are being driven into a wall with a crash test dummy. In one car, the dummy is wearing a seatbelt. In the other, it isn't. You saw this kind of thing in grade 11, and I'm sure it's been drilled into your head. You got to wear your seatbelt. Let's see what happens. Okay, so you see what happens if you're not wearing your seatbelt, X underscore X, or if you're wearing your seatbelt equals D. What the heck? Oh, I get it. I get it. This is a not happy face, and that is a happy face. Right. Wear your seatbelt, get a happy face. Don't wear your seatbelt, get a very unhappy face with X's in your eyes. You see what happens when the driver's not wearing his or her seatbelt. He ends up smashing into the dashboard and the windshield. But when he is wearing his seatbelt, and especially when the airbag deploys, he ends up relatively safe. Why is this? Let's just go back for a moment and imagine what's happening here. You learned in grade 11, once again, about Newton's first law, N1 as I like to call it. How would you have explained what's going on here? Well, in this scenario, if you think back to grade 11, we like to say that the dummy kept on going forward, but the car stopped. Why do we say this? Well, we say that the dummy kept on going forward because of his, whoops, there I go zooming again and have, wow. As you guys know, every now and then I zoom to 5 million% and have no idea why. Okay. Nice recovery there, Ackerman. Thanks. Okay. Back to what we were saying. Why does the dummy keep on going forward here? You learned in grade 11, it's because of his inertia. Because of his inertia, he wants to keep on going. But the car stops. Why does the car stop? Because the car has an unbalanced force. So it stops. But the dummy keeps on going forward. And what happens when the car stops and the dummy keeps going forward? Bang, you hit the dashboard, and that is a big ouch, or X underscore X, right? What's going on in the second example? Here, you learned in grade 11, when you studied Newton's laws, that the dummy decelerates at the same rate as the car. Why? Because, B/C, because he's wearing a seatbelt. In other words, the same forces that slow down the car when it hits the wall are being applied to the dummy's body, and the result is the same acceleration or deceleration here. Okay? Well, let's see if we can draw the free body diagrams for both of these scenarios. For example, if you're watching this motion from Earth's, let's do it from Earth's frame of reference. When you are not wearing a seatbelt, what does the free body diagram look like if you watch this motion from Earth and the dummy is not wearing a seatbelt? In other words, the upper picture here. Take a moment to try to do that. Really think about this. What does this free body diagram look like from the Earth's frame of reference for a dummy not wearing a seatbelt? Pause the video, try to draw that. Okay, so now we're back. If you're in the Earth's frame of reference, what are you going to put here? Well, you're going to put gravity for sure, Fg. And you're going to put the normal force for sure because the dummy is sitting on the seat for sure. These two are equal. And in fact, that's all you're going to put because you're going to realize that the dummy keeps going forward because of his inertia. There's no force slowing him down, and so he crashes into the wall, or the dashboard rather. However, now I want you to think about the last time you were in a car. Perhaps you had the misfortune of being in a car accident, I hope not, but I think most of us have felt what it's like when the driver slams on the brakes very suddenly. Think about what it feels like if you're in the front seat and the driver hits the brakes really, really hard. And then use that memory to draw the free body diagram. Okay, so ready? Free body diagram from the car's frame of reference. Okay, if you are not wearing a seatbelt, which you shouldn't be doing, but anyway, what would you feel? Do you remember what it feels like when the driver slams on the brakes? Pause the video and take a moment to try to draw that. Okay, so we're back now, and we're going to draw this same free body diagram. What's it going to have? Still going to have gravity? Yes. Still going to have the normal force? Yes. They're going to be equal. But when you're in a car where someone has slammed on the brakes or you've actually hit something, you lurch forward. You feel yourself being forced forward. So what do? You add in another force. But now I'm going to ask you, what force is this? It's not one of the four fundamental forces. It's certainly not gravity, it's not electromagnetic, and it's not nuclear. In other words, it's a question mark force. We have a name for this kind of force, and we call it a fictitious force for the reasons that I explained earlier. You got to make it up if you want to still believe in Newton's first law. Or you can look at the motion from the point of view of the Earth's frame of reference. No fictitious force is needed. It's just Newton's first law in action. Or you can get rid of the fictitious force idea by just saying, okay, well, throw your hands up. I guess Newton's first law doesn't apply in this frame of reference. All right, so there's a number of ways to view motion, and they do involve fictitious forces or the abandonment of Newton's first law. All right. Now, I know what I just said was, there's a lot of confusion going on. If you feel confused right now, that's totally normal, and you might want to review the video or just sit and think about it for a bit. But what I'm going to do is move on now, and we're actually going to use this idea. We're going to wrap up by solving a problem, or at least getting you started toward a solution. This is sample problem 2 in the section, in which they say, a teacher suspends a small rubber stopper from the roof of a bus. I don't know, I guess some teachers do this in their spare time. It says, as in figure 3a from the chapter opener. So the chapter opener, if you're following in your book, just means the very beginning of chapter 2. So I went and dug up figure 3 for you right here. It shows a school bus, and it says there's a pendulum, a mass hanging from a string, a pendulum-style accelerometer. We're going to see how a simple mass hanging from a string can actually act as a device that measures your acceleration. There are 3 possible orientations for the accelerometer: I, J, and K. What are these 3 scenarios? Can you guess? Forget about I for a moment. How about J? When would the accelerometer swing backward? Can you guess? Take a moment and think about it. If you guessed that when the bus accelerates forward, the stopper swings backward, that would be the same as thinking about what I asked you to try as a little mini experiment tomorrow on the way to school. I told you to try sitting in the passenger seat while someone else drives, and as the person accelerates forward from the red light that turns green, drop a mass and see what happens. It won't fall straight down, it'll sort of fall backward toward your belly. Same thing's going on here. Bus accelerates forward, rubber stopper swings backward. Now can you guess what this picture represents? Take a moment and pause the video and think about it. Okay, we're back. And if you guessed, hey, this is actually just the same thing we looked at here. This is like a person feeling forced forward when the car stops suddenly, then you're right. It's the same situation. This happens when the bus accelerates backward. In other words, there's an interesting relationship. Rubber stopper goes back, acceleration is forward. Or rubber stopper goes forward, acceleration is back. So right away, a simple hanging mass gives us an idea of the direction of acceleration. It's opposite the direction that the rubber stopper is hanging. And so to wrap up our preliminary analysis here, when would the rubber stopper just not be hanging at an angle? When would it hang vertically? Take a moment and take a guess. Okay, now we're back. If you guessed that this is when the velocity is constant, then you are absolutely right. In fact, this is the only time that physics looks the same on the bus as it does on Earth. Rubber stoppers hung on Earth hang straight down. They should do so in a bus, but they don't always, right? Like in here, in J and in K. When don't they? When we're accelerating. So the force situation, the Newton's first law situation, is different when you're accelerating. I guess these are non-inertial frames of reference. And I guess that means this is an inertial frame of reference, constant velocity. All right, let's see how we can solve this, and then I'll let you go because I know it's been a long one, but it's a tricky concept. Here we go. The suspending cord makes an angle of 8.5 degrees from the vertical as the bus is accelerating forward. So here's what we can do. In the bus frame of reference, we're going to draw ourselves a free body diagram for a hanging mass that is hanging at an 8.5 degree angle as the bus accelerates forward. So let's call this the forward direction. If this is the forward direction, then we know from our pictures here that this mass will hang backward at an angle. And so the string will look something like this, where here's the vertical, and the 8.5 degrees is right in here. What would be the forces acting in this frame of reference? Well, certainly tension will be acting. We have a string, and so that goes this way. What else will be acting? Well, certainly gravity, because we are on Earth, so we're going to have the force of gravity. That's easy enough, nothing too tough there. But also, for reasons we discussed, we're going to put a fictitious force in going backward, because in this frame of reference, the only way to believe in Newton's laws and still explain what's going on is to imagine a fictitious, that's not friction, but fictitious force backward. So here's the bus free body diagram. Now let's try drawing the free body diagram from the Earth frame of reference, from someone who's just standing watching. And remember, think about what we discussed back here. When you watch some acceleration from Earth, you don't need fictitious forces. You understand that the motion is due to Newton's first law, because you are in an inertial frame of reference. So, if you look at what we did here, the free body diagrams were really the same. The only difference was we got rid of the fictitious force. Well, guess what? We do the same thing here. We're going to draw that same rubber stopper. Is it going to hang at an angle, even in the Earth frame of reference? Sure. Watch a car go by where something's hanging from the ceiling, like maybe those fuzzy dice that some people have hanging from the ceiling or from the rearview mirror of their car because they're stuck in the 1970s. All right? See what you get there. It really does hang at an angle in both frames of reference, 8.5 degrees. That doesn't change. Therefore, the tension force is still the same. Gravity, of course, is still the same. But all we do, as you saw in the case of car accidents that we watched a moment ago, all you do in the Earth frame of reference is you get rid of the fictitious force because you don't need it in the Earth frame of reference. In the Earth frame of reference, this thing's hanging at an angle because as the car accelerates forward or the bus accelerates forward, the inertia of this mass makes it want to, quote, want to maintain its constant velocity, which was whatever the initial velocity was. Let's say 0 if you were waiting at a red light for the light to turn green. However, once the car accelerated, the mass, which, quote, didn't want to come along for the ride, it wanted to maintain a constant velocity, it ended up getting tugged by the string and kind of lagging behind. And therefore, we ended up with this 8.5 degree angle. And so what I'm going to do next, and this, I promise you, is the grand finale, we're going to take this free body diagram and we're going to just paste it in to this new window right here. And let's look at what we can do. Once we have this free body diagram, can we possibly solve what's going on? Yes, we can write Ft equals something, comma something. What's it going to be? Ft, that's going to be actually a sine of 8.5 degrees. And it's also going to be an Ft cos of 8.5 degrees. What is gravity? Gravity, of course, as before, is 0 in the x direction, negative mg. Those are the only two forces, so they are equal to F net. Now, what do we write for F net? There is acceleration in this question. The question is, what direction is it in? Well, there's no acceleration for a bus driving along the road in the y direction. The bus is accelerating horizontally, and therefore so is the mass, which means everything, ma, is in the x direction. What do you do now? Same thing we've always done with these. We're going to make an x equation, and we're going to make a y equation. And this is where I'm going to leave you guys off to solve the rest of this on your own. Your textbook does it for you as well, but you're going to get down to a point where you can actually solve for the acceleration, and it'll be based on the angle. And interestingly, it'll be based on the angle only. Work out the algebra here, and you'll see that the mass cancels out. Are you surprised? We've seen it cancel out a number of times in this course, so I hope you're not. But that's it for now. You got a little bit of extra work to do here, and I'll see you guys in class. Thanks for watching.